This video covers the review for section 4.3 in trigonometry, vectors. Given the vector u equals negative 9i minus 6j, let's sketch that vector and name the quadrant. So remember, I is the unit vector in the positive x direction, j is the unit vector in the y direction. They're unit vectors, and when you multiply them by a number, it increases their length. So negative 9i would be negative 9 to the left, negative 6j will then go 6 down. It's a lot like plotting the point, negative 9, negative 6. Instead of thinking of it as a point, we think of it now as having a distance from the origin and then an angle that rotates it around to that actual spot. So we think of these as these lines that rotate, these directed line segments that rotate from the positive x-axis. So we say that's in quadrant 3. The magnitude of that vector is simply just its length from the tail to the tip. Tail to the tip. And so if we think of this as a right triangle, the distance is from tail to tip. Magnitude. And we like to say for magnitude, we like to write the double bars around the u. Now you'll typically see math teachers use an arrow above it to say it's a vector, but in type, we see it in bold u. So the side here is length 6 and the side here is length 9. So we know Pythagorean theorem says the length of u is the square root of 6 squared plus 9 squared, or 36 plus 81 square root of 117, which is approximately 10.82 units long. Now we do what we were doing before and talk about the reference angle versus the angle theta. Theta is obviously bigger than 180 degrees, but the reference angle theta ref, that's just this angle here, which says that the tangent of theta ref is the opposite over the adjacent, giving us theta ref is inverse tangent of 3 goes into 6, 2, and 3 goes into 9, 3 times. Inverse tangent of 2/3 gives us around 33.69 degrees. The theta then is 33.69 past 180. Theta is theta ref plus 180 degrees, putting it in quadrant 3. And so on that one, we get 213.69 degrees. Okay, so that's the idea of a vector having a direction designated by theta and having a magnitude 10.82. When we graph a vector, we always take its initial point to be at the origin, called the tail, and then it goes to some tip depending on, what quadrant it is in. In this example, we're saying that this vector is equivalent to the vector we want from the origin out is equivalent to the vector that has a starting point of -5, -2, an ending point of 12, -7. Now we take that vector and we translate it to the origin, maintaining that same slant or slope to it. So the way that we find the coordinates of this ending point are A is x2 minus x1, 12 minus a minus 5. What it is just saying that as if this thing started off at -5 and ended over here at 12, then that means that's 17 to the right. So the vector then that starts at the origin is going to have to go 17 to the right. And we see now that the y values started off at -2 and went down to -7. So we take -7 minus a -2. From -2 down to -7, we've gone down 5. So it really is just rise and run from algebra. So the vector v then is 17 units to the right of the origin and 5 units down from the origin, 17i minus 5j. So remember, vectors, any vector that has a starting point and an ending point that maintains that same out 17 and down 5, they're said to all be equivalent vectors. The one that we always use, though, is the one that has the starting point of the origin and goes to the right 17 and down -5. Okay, so again, we can describe a vector in terms of its rectangular coordinates, out 17 and down 5, or we can define the vector by saying that its magnitude is 10.82 and its angle is 213.69 degrees. So that's what this one's saying. We've got a vector v whose magnitude is 45 units, but the angle on this is 340. So it goes all the way around past 270 to 340. And its magnitude is 45. So there's the end, there's the start. And now we want to write this in AI plus BJ. So we want to know how far out right you have to go and how far down we have to go. So in order to find that, we set up that right triangle that you see there and call this B and call this A. And this length of the hypotenuse is 45. All right, so remember, we said the angle is 340, but then what's the reference angle? That's this guy right here. 360 minus 340 puts us at 20-degree reference angle. So then, A will be found by doing cosine equals A over 45. B will be found by doing sine giving us A equals 45 cosine 20. B is 45 sine 20. It doesn't take long to get used to the fact that A is the 45 cosine and B is the 45 sine. That pattern becomes readily apparent quickly. So A to one decimal place this time, 42.3, and B is 15.4. Should make sense. I didn't draw this too perfectly. 20 degrees should have been substantially smaller than that. And that's why B going down only 15.4, but going right 42.3. So now we can write the vector V in terms of what we call its components, 42.3 to the right. And this case, we got to remember that B is going down 15.4. The next one is just some simple vector arithmetic. What's nice about this is it feels just like algebra. It says, let's take 4 times vector 1. Remember, 4 times a vector, a scalar times a vector, all it does is take your initial vector, which goes out 8, down 3, and it just makes it 4 times as long as the original vector. It scales it. It's called a scalar. It scales it differently. So we're going to take 4 times that vector, negative 8i minus 3j. And then we're going to subtract 2 times vector 2, negative 6i plus 7j. So as would be expected, you just distribute the 4 across and then the negative 2 across. And you can only add the I components to the i's and the j's to the j's. So negative 32 plus 12 is negative 20i. And negative 12 minus 14 is negative 26j. So there's the vector for vi, or v1 minus 2v2. All right, so let's think about this one. It's going out 20, and it's going down 26. So we would expect that the direction of this is bigger than 180 and smaller than 270. And the magnitude of it if we're going out 20 and down 26, the magnitude of 4v1 minus 2v2, this is equal to the square root of the sum of their squares. Which gives you the square root of 404, which is approximately 20.1. So that's its magnitude. Its direction is theta. But we're going to find theta reference first. And so theta reference, once we find it, we add that to 180 and that gives us theta. So when we look at theta reference, sine of theta reference is equal to opposite over adjacent, 26 over 20. So theta reference is the inverse sine of 26 over 20. So we use our calculator on this one and calculate the inverse sine of 26 divided by 20. Oh, sine, yeah, that's not going to work. That was supposed to be a tangent. Inverse tangent of 26 divided by 20 is 52.43 degrees. We'll use 52.4 degrees. And now theta, or the direction, is 180 plus 52.4, which is equal to 232 plus 4. So the direction, theta, is 232.4 degrees. All right, we throw the word unit around a lot in mathematics, and unit means a lot of times 1, or in this case, a unit vector has length 1. It's the idea behind this unit vector that we're looking for. It goes left 5 and then down 12. And so if we think of this as a right triangle, 5, 12, we should recognize that hypotenuse as being length 13. So we don't want that vector. We want a vector that is merely identical to that, but just has length 1. So we want to scale it back to make it have length 1, so it's on the unit circle then. And the way you make anything have length 1 is divide it by its length. If I have something that's 5 units long and I divide by 5, then it'll have length 1. And so this vector v, if we divide it by its length, it'll make the vector be in the same direction, but it'll have length 1 or be a unit vector. So we take negative 5i minus 12j and we divide by the length of v. Remember, the length of v is found by taking the square root of the sum of those two squares. 25 and 144 is 169, or 13, but we're supposed to recognize that Pythagorean triplet pretty quickly. And so we take these and divide by 13, and that gives us negative 5/13 I minus 12/13 j. And now this is a unit vector that's in the same direction as v. We love to write headings of planes and boats as vectors. They have their heading on a direction of 210 degrees. And it's traveling at 555 miles an hour. We make that the length of the vector and use the fact that it's a theta equals 210, or theta ref is 30 degrees. And then we write a vector with that, with those details, a length of 555 on a heading of 210 degrees. So we know the length of this vector, and so we draw the triangle with the length of that vector. So we know this length 555, we know this angle is 30, and then this is always the A, and this is always the B. We got to be careful though. We're going to find them in absolute value, and then we're going to have to put the negatives on them. Okay, so to find A, the cosine of 30 is A over 555. The sine of 30 is B over 555. Or A is equal to cosine 30 times 555. And B is sine of 30 degrees times 555. Now we know what these things are. They're root 3 over 2 times 555 and 1/2 of 555. So 555 divided by 2 is 277.5. Now 555 times cosine of 30 is 480.6. Didn't tell us how many spaces to round to, so we'll just do one decimal space. Okay, so that's A in absolute value. So we need to use negative 480.6. And B, we need to use negative 277.5 because it's in quadrant 3. So this vector heading in rectangular coordinates is negative 480.6 I minus 277.5 J. So what do you do with something like that? Well, the next problem says a plane is traveling with that heading. So we've got the plane that's traveling with that heading. And there's a strong wind at 45 miles an hour with a heading of 270. So then there's wind. The vector is substantially shorter than that because it's only 45 miles an hour. And then find the true heading and speed of the plane. Well, if the plane is trying to go down and you have wind that's also pushing it down, it's going to take it further down. So the resultant of these two vectors, by adding them together, is going to be the true heading and speed of the plane. So true direction or heading and speed. We have to take and find the resultant. The plane is negative 480.6 I minus 277.5 J. The wind is, well, this is in the J direction down, so negative 45 J. So from there, we're going to sum those two up, and that's going to give us the resultant so that we can find the true heading and true speed. So we take the plane plus the wind, which is negative 480.6 I minus 277.5 J, and then minus 45 J. So the wind only affects that J component. This negative 480.6 doesn't get affected. And so this gives us negative 322.5 in the J direction. So that's the plane plus the wind. Now the true heading now that we know the resultant vector is left 480.6 and down 322.5. We want to know the length of this vector. So for the speed of the plane, the heading of the plane, theta reference, is going to be found by using an inverse tangent. So we see that the reference angle theta tangent to that angle is 322.5. Divided by 480.6. And so we take the inverse tangent to that. And that gives us around 33.9 degrees for a reference angle. So that means the true heading theta is 180 degrees plus 33.9, which gives 213.9 degrees for the true heading. So we see that it was going 210 degrees and it knocked it off by 3.9 degrees. So you do that for a few hundred miles, it's going to get you way off track. You got to be careful about these things as a pilot. Now, what's the true speed? The speed of the plane is the length of v plus w. Plane plus the wind. And so we know that's equal to the square root of the sum of the squares. 40.6 plus 322.5. And that gives us around 578.8 miles an hour. So that 45-degree wind helped us out pretty substantially there. So 578.8 miles an hour. This says this would be advantageous for the plane, save a little gas because they're going a little faster. (22, 3 miles an hour faster. And this concludes the video for the review for section 4.3 in trigonometry, vectors.